Okay, hi everybody. Your only homework for tonight is to go over the most recent homework with me. This is homework we did not go over. This was the homework on series, I think, infinite series. Okay, why am I doing this? So I'm keeping this homework very, very light because, as I said, we're entering this last unit of ours, and it is definitely one of the most challenging units that we will be studying. But my goal is, if we make sure we are incrementally keeping on top of things, it really should not make it difficult at all. Okay, so this screencast is about going over this homework from right here, and I want you all to take it out and then take any requisite annotating notes. Tomorrow in class, I will not be there. Tomorrow I'm out all day because I'm attending a funeral. Nothing dire, nothing major. I mean, it is a funeral, but it's circumstances that are not painful. So I am not going to be here. There will be a lesson tomorrow on a screencast. So you are all required to report to class, to listen to the lesson, take notes on it, and then do the homework. Okay, so it's very, very important that that you kind of heed my plan that I'm breaking down for you. There will be someone in the class tomorrow to take attendance and so forth, and let me know how it goes. Okay, so let's take out this homework, please. So questions number 3 and 5 are asking about what these two series equal. So you're adding up an infinite number of terms. Now, these two series here, I wrote down, these are actually geometric series, but they're in disguise. Last class, when we were taking notes on that outline that I gave you the general look of a summand when you're talking about a geometric series. But sometimes the summand won't look exactly like that, right? Sometimes it will be simplified, or sometimes it will look slightly different. The question I'm always asked is, if the summand of an infinite geometric series is not written in the form of the summand that we wrote down, how do I recognize the series are geometric? And here is my answer. The way you recognize an infinite geometric series, I always, and you will do this from here on out, I hope, I always just do a mental check. And a mental check when it comes to infinite series is I plug in the first few terms of the sum, because within a couple, you will probably see, oh, it is in fact a geometric series. So here is number 3. I inputted in k equals 1, k equals 2, k equals 3, k equals 4, right? You see relatively quickly that each of these series is in fact geometric. Here is number 5, the first few terms. So to answer the question, how do I recognize series that are geometric, that are in disguise? Input in the first few terms, and it will become readily obvious to you. Now, let's take a look at number 3 and 5 here. Once I recognize the series is geometric, I need to find R, because not every infinite series that is geometric will converge. Only if R is between -1 and 1 will the geometric series converge. And if the geometric series converges, right, this is the convergent value. It's a sub 1 all over 1 minus r, or the first term divided by 1 minus r. So this equals the sum of all of these infinite terms. Similarly here, this equals the sum of all of these terms, okay? All right, here's number 7. Number 7, if you kind of followed my advice, you said, okay, what kind of series is this? When you plug in a few terms right down here, right, you'll probably readily see this series is not geometric, it's not arithmetic. One side note to remember is that every arithmetic series, every infinite arithmetic series diverges. And do you remember the reason why? We talked about this in class, okay? If you don't remember, please consult your notes or talk to someone right now, ask someone a question. I'm not going to give you the answer straight away. I want you to kind of think about it. So right away, you recognize this series is not geometric. What on earth do you do? And I wrote, this was supposed to be a thinking question. Of all the questions last night, this was the one where that probably would have stumped you. I'm going to come back to it and to kind of show you how to do it, but I fully expected this would have stumped you. You would have kind of stopped here and said, what on earth do I do? This would have required some creativity, some time on your hands to think about it. But maybe you said, okay, I'm going to come back to this. Let's take a look at 31. I just did 31A and C. 31A and C, I think it asked you to find the values of X that will allow for this geometric series to converge, this infinite geometric series to converge. The first thing I did was I found out what R is. So the series is in fact geometric. I know the series will converge if R is between -1 and 1. And look what I did here is I just divided by -1 and I'm here. I'm guessing some of you stopped here and said, what do I do? It's just algebra, okay? If some number squared is between -1 and 1, first of all, you know that a number squared will never be negative. So really this interval of x squared could be even made smaller by doing this. Okay, that if, we can actually equal 0 too, because 0 is between here. So really, since we know x squared will never be negative, I can make this interval shorter, because really, the only thing x squared is going to be between is 0 and 1. When you take the square root, you have this interval of x. So this right here is the range of values for x that will make this infinite geometric series converge. A similar thing happens here in 31C. Here is the infinite geometric series. It is geometric. I have to find what R is. I know the series will converge if e to the negative x is between -1 and 1. But you know e raised to a power, not only will this number never be negative, it will never be 0. So this interval can be shortened to here. Okay, here I'm not including 0 because e to the negative x cannot equal 0. Okay, so now we're at the point where e to the negative x is between 0 and 1, right? And what that means is the following. We have to, in the end, get to the point where we're saying what x could be, correct? So we need to somehow write this inequality in terms of x. There's a couple ways you could have done this, but I'm going to show you this way. You know that e to the negative x, if I were to graph y equals e to the negative x, that looks like an exponential decay function. Wouldn't you agree? Okay, and if I think about this exponential decay function, it has a y int of 0. For what values of x will e to the negative x be less than 1? Well, it looks like here, as long as x is greater than 0, e to the negative x will be less than 1. So at the end of the day, your final answer is for values of x, whoops, what did I just do? For values of x bigger than 0, the infinite geometric series will converge. So I wrote here, for values of x bigger than 0, those values allow for convergence. Okay? Number 32. This question asked you to prove that this sum, and again, note the ... here, okay? This infinite sum equals this. Well, let's take a look. An infinite sum, let's see, this series is geometric because r is -1/2 sine x. Well, we first have to prove that this value of r will even allow for convergence, which means that this value of r will even allow for an infinite sum to exist. So we have to prove that this value of r is between -1 and 1. Well, let's see. Since we know sine x exists between -1 and 1, it must be the case then, if I multiply all three parts here by -1/2, because that's what r is after all, then this inequality becomes this one. Sine x is then, whoops, I lost my -1/2 here. -1/2, right? -1/2 sine x, which is r, right? This r value is between -1/2 and 1/2. And any value between -1/2 and 1/2 will be between -1 and 1. So therefore we know this geometric series must converge, right? Okay, well then what's the convergent value? A sub 1 over 1 minus r. And then it's a matter of just simplifying to get to the final answer. Okay, so that is it for homework. Enjoy the light night. Please, please, please make sure that you went over this homework with me very carefully. Oh, number 7. Okay, number 7. But I still may finish my thought. Just please make sure you annotate and you take good notes on your homework. If you had any issues with this, even if you didn't, I'm sure I said something that was an aha moment for you. At least write those down. All right, number 7. You are left here. Okay, maybe you are looking at this and you say, you know what? I kind of recognize rational expressions like this, and I kind of remember we used to do something with them. And here's what we did. When we had a rational expression back in the day, one thing that we did was decomposed it, right? And the reason why we even undertook this task of decomposing was because we were trying to anti-differentiate. Now, we're not anti-differentiating here, but we could try and decompose, because if we decompose and re-express the summoned in a different way, maybe I'll get a series that presents itself in a way that will somehow make me able to figure out what the sum is. So here is me decomposing, okay? Decomposing a rational function, and ... If you do this correctly, the work here, this is old news, you will get a equals 1 and b equals -1, which then really tells me that the original summoned could be rewritten like this. And so the original series, this infinite series, could be rewritten like this. Well, let's see if it makes a difference now. Let's write out a few terms and see if it makes a difference. Okay? When I plug in k equals 1, I get 1/3 minus 1/4. That is the first term. Plus. Okay. The next term is going to be, plug in 2, 1/4 minus 1/5. Right? Plus, let's see. Plugging k equals 3, 1/5 minus 1/6. And maybe you're someone who doesn't see what's happening yet. Let's plug in k equals 4, 1/6 minus 1/7. Oh, let's just put a ... here for a second. Now take a look at this. If I write out the terms in this re-expressed summoned, do you see what happens? -1/4, +1/4, -1/5, +1/5, -1/6, +1/6. Now, how many terms are we adding up, everyone? Infinite. That means this will forever and ever go on, right? Which means every single term forever and ever will forever cancel. What's left though? Oh, this lone 1/3 is left. So in this case, this series, it's not geometric, it's not arithmetic, but with some fooling around with it, I'm able to see that the series does in fact converge to 1/3. Okay, now this kind of series is not one that I'm ever going to test. It's not one that you're ever going to see on the AP exam. I thought it was kind of fun. This kind of series, if you were curious about the name of it, the name of a series where when you re-express it somehow, terms just start dropping like flies. This is called a telescoping sum. Right? It's called a telescoping series, actually. A telescoping series is one where this kind of happens. It's kind of fun. Okay? All right, that is it. So again, tomorrow in class, come to class, you'll have a lesson. We move on with our series and sequence conversations. And again, if we are doing what we should be doing on a daily incremental basis, this last, probably most, I would say, most challenging unit should become infinitely doable. Okay, have a good night.